In this video, I'm going to show you another analysis method that you can use in SOLIDWORKS using a model from a previous example. By the time we're finished, you're going to get a chance to see some dynamical modeling of different modes of vibration of a structure, and that's not something that you've encountered before. However, it's an important and valuable design insight, particularly if you're designing something that will go on, say, a spacecraft or a car or anything that moves. So here we are with this bracket that you've seen already, and I'm going to create a new study, and the study will be a frequency study. Now keep in mind, all I've done in terms of the mathematics is create the same model, but now I'm using a different set of governing equations. I'll just double check the material. So I've applied 6061 T6, which is a standard aluminum alloy that you'll encounter. I have to go back and do the fixtures again. Now I'm going to mesh this, and I'll create the mesh similar to what you've seen before, but I'm not going to be quite so fussy. I'm not going to apply any external loads. I'm going to run the study. So the reason I didn't apply any external loads is because this is as a frequency study. All I want to see is what's going to happen from the part's intrinsic behavior itself. And so the scheme here is you get multiple amplitudes at different modes. Now we can look at this mode, and you can see this is the side-to-side wobbling mode, which will occur at 528 hertz, as you can read up here. We can look at the next mode, which is it's a side-to-side with a bit of a twist, and that's going to happen at 1000 hertz frequency. The next higher mode is this mode, and that's at almost 2000 hertz. Now keep in mind the scale is exaggerated in these. The important thing to know here is the scale of the deformation and the frequency. We can look at 2700 hertz for the next mode, and you can see that's the weird geometric shape that it would be wiggling at in that mode. And the fifth mode would be another complicated shape, and that's at 3000 hertz. So what was that? Because that was weird. It showed us all these woggling modes. We didn't apply a load to the structure. Really what we were looking at was the structure's intrinsic behavior in vibration. Now, the first thing that you'd want to know is what are the frequencies that each of those modes occur at? Because if you have a motor or wind or some vibration source that's close to those frequencies, then it's going to excite that part. So you've all experienced driving down the highway in a car and having a part rattle on it. Well, that's because there's something driving that natural frequency of that part that just makes the device rattle just so. So this simulation tool allows you to find what are those frequencies where the part you've designed is going to vibrate and rattle. Then you can look and see at each of those modes how much the deflection will be for a given amount of energy. And that's going to tell you what you have to worry about in terms of the structural deformation. Then, just as in the previous static case, you can go back into your part design and make a few relatively minor changes and see if you can improve or change that frequency. You can change the amplitude of it, and that will make it vibrate less. And you can change the frequency of it to essentially detune it from the driving force. In general, if you make a part stiffer, its frequency that it will vibrate at will go higher. And you can make the part so stiff that any of the forcing frequencies are too low to really excite it. Or you can actually try to damp that particular mode of the vibration and get the energy down. All this comes back to the shape and size and materials and mounting of the part itself. So you can use your finite element modeling to tell you some interesting things about how the part will behave and how to improve your design. And with one final note about this frequency analysis, I want to show you one of the cool things that you can do in SolidWorks. So in SolidWorks, because you've done the frequency analysis of the first 5 amplitudes, you can also right-click on the analysis and do animate. And you can see what it's actually doing in terms of the simulation. So if you're wondering what the mode was that it was vibrating in, that's how you can see it.